So good afternoon, everyone. It's Janelle Bates with the Ontario Waterpower Association. I see we've got about 20 attendees currently logged in. We'll just give some folks another couple minutes to make sure we have everyone signed in. We have about 52 participants, so we'll get started here in a moment. I do have our presenters on the line that are waiting to start the presentation, so we'll Jillian and Keenan will give them another probably 2 minutes, and then we'll get going. All right, so we've got a number of people already signed in. So in the interest of your time, we're going to get started. So welcome, everyone. Welcome to our webinar. My name is Janelle Bates. I'm with the Ontario Waterpower Association, the Director of Member Relations and Events. And joining me today is Jillian Davis and Keenan Goslin from Kleinschmidt. So we're really pleased to have those folks here to present to us. For those of you that are not familiar with the Ontario Waterpower Association, we're an industry advocacy association. We represent 95% of all generators in the province of Ontario and the product and service providers that support those generators, such as Kleinschmidt. So we're glad to have you with us today. We have about 140 members, member companies, I should say, and a network of about 350 contacts within those member companies. We coordinate webinars such as this to highlight the services of those members, as well as to exchange ideas and build capacity within the industry. So if you're interested in presenting at a future webinar, or you'd like to learn more about our association, you can follow up with me after the webinar, and I'll also be sending out a short survey, which you can complete as well. So just before we get started, a few housekeeping items. All of your lines are muted individually throughout the presentation. We will be opening up the presentation at the end for questions from the participants. There's two options to ask your questions. You can either use the raise your hand icon, which can be found in your toolbar, or you can type your question into the question box and I will read your question to the presenters. You should know that this webinar is being recorded, and you will receive a copy of the recording after the session, so that'll be sent out probably sometime next week. And so you will receive both the audio and the presentation. So now it's my pleasure to introduce your presenters from Kleinschmidt. We have with us today Jillian Davis and Keenan Goslin. So Jillian and Keenan, I'm going to turn things over to you, and you can continue with the presentation.
Thank you, Janelle. We're happy to be here. I'm Jillian Davis. I'm a senior engineer with Kleinschmidt Associates with over 12 years in the hydro industry, working on dams, powerhouses, penstocks, gates, pretty much everything hydro related. And one of my specialties is penstock. So I've done over 50 different penstock related projects, from inspections to repairs, replacements, and also design of new structures. I've presented on technical papers relating to penstocks before, twice at Hydrovision, and am one of the co-authors of the paper Taking Stock of Your Penstock with Keenan that this presentation is based on.
Thanks, Jill. Excuse me. Yeah, I'm Keenan Goslin. I'm also a senior engineer with Kleinschmidt Associates. Similar experience to Jill, working across all of hydro, but again, specializing in Penstocks. And I work again with inspections, repairs, design of new structures, including materials of steel, FRP, HDPE, and some concrete. So we're here to talk about Penstocks, right? So hydro plant owners nowadays have numerous financial, operational, and safety issues to deal with every day. Requires continually assessing, what's critical for that day, and what's most important to keep that facility running smoothly and profitable for today and into the future. What is kind of important to think about, though, is Penstocks are kind of viewed from what I've seen as a kind of a constant. They're unchanging, long standing structures, no moving parts. They're kind of just there getting the water from the dam down to the powerhouse, and then we think of them having a low risk of failure or having a less of an impact on the structure, on the plant and facility. The issue there is that many Penstocks are getting into or beyond their length of the service life or their design life, right? So we're also asking a lot of these structures. We've potentially changed as the industry changes and the needs for different generation assets change. We're putting higher demands on the Penstocks, potentially having more starts and stops, more unit trips, pushing the pressures into the Penstocks maybe a little bit higher than they were designed for, which makes it even more important to understand the condition of our Penstocks. So on the other side of that is we're typically seeing less regular physical inspections, so operators not as commonly going out daily, weekly, looking at them. We're trying to replace some inspections with remote monitoring, and that remote monitoring, from what I've seen, is typically looking at flows and pressures and trying to detect an issue as it's happening, right? And saying, is it a safety concern, and whether we need to do something about it right then. But that doesn't always address or detect deterioration in the Penstock. So what we're thinking about and advocating for is trying to be a little less reactive, trying to detect that deterioration ahead of time instead of detecting a problem as it's happening. We see that to improve long-term reliability and safety of the structures, resulting in cost-effective use of our facilities, because the Penstock is a vital part of our hydro plants. And trying to extend the service life of our structure, right? So the longer we can create a cost-effective Penstock or maintain that Penstock, the overall cost effectiveness of our plant and cost of energy is going to go down. So, we're pushing, we support having a Penstock safety program, which you can talk about ways to, extend that service life and maintain a safe and reliable Penstock.
So back in the day when these Penstocks were initially built, the stations were likely manned with an operator there 5 to 6 days a week. As Keenan kind of mentioned, they were doing visual inspections of their Penstock system on a regular basis, possibly weekly, able to easily get out there after a seismic event or a windstorm or some other change in weather that could impact their pipe. And they were looking at coatings. They were able, with their wood safe pipe, they were looking at the condition of the wood. They were able to see a lot. Now, in today's world, stations aren't always manned. Some still are. A lot of times they're controlled from a central location with an operator assigned to the station, but the operator has multiple projects they're responsible for, and therefore they might spend a day at the site each week. maybe a little bit more, maybe a little bit less, but this gives them less time to just see things and understand what's going on. So it just happens that some stuff can be missed and issues can remain unidentified until they become significant and sometimes result in a failure. Next slide. So what might this remote monitoring miss? Again, remember, remote monitoring is usually some sort of pressure sensors or flow sensors within the system. And so you're just looking for changes. If those changes are occurring, you already have a substantial leak, maybe even have lost your penstock. So some stuff that's missing is overstressing and buckling of your saddles, especially at the saddle support, foundation failures, minor damage caused by those earthquakes I mentioned, trees falling on your penstock. If you're on a cliff edge or on a mountainside, you could have rocks. And then there's the subtle signs of surface deterioration you can see from the outside. Wood stave penstocks are looking for corroded wood staves, bands, steel, you're looking for paint missing, pitting developing, rusting, fiberglass reinforced penstock or FRP, you're looking for delamination. And then there's the internal issues that you can't see unless you dewater your penstock and go in and take a look at it. And you're looking for the same surface defects that you would bought from the exterior. But if your exterior could look fine and your interior could look really terrible, and if it's buried, you're not seeing it at all unless you're going in there. Next slide. So these next few slides are just some examples of some penstock failures that Kleinschmidt has seen over time. This first one in this picture, it's mostly a buried steel penstock. It had a section in the crawl space of the powerhouse that was exposed. And at some point, they developed a leak in the invert of that penstock. That leak was never found, and eventually it tore wide open. It eroded a lot of area underneath the powerhouse, came out into the parking lot area of the building, and took out the parking lot until it finally went into the tail race. And it took them a long time for that gate to go down, and it took quite a while for the repair to be made to fix this and get this back in operation. Next slide. This next site had a FRP pipe that was underneath the parking area upstream of the powerhouse, and that pipe failed. This is a pipe that was never inspected. It's very possible that if it had been inspected, that they could have seen some signs of delamination from the inside to know that they needed to do a repair, but it is FRP pipe, so it's also possible that that change from no signs to failure could have been very quick, and even with an inspection program, they might not have seen this. But once the FRP pipe failed, significant amount of head, developed a high pressure water spout that took off the siding on the powerhouse, destroyed the inside of the powerhouse, and of course it washed out the entire area upstream down into the tail race, and this place was offline for nearly a year before repairs were made. This example here, the penstock is exposed. It had thinning steel and was dewatered for several days for work, and it was hot, high temperatures. When they let the water back in, and it was with the cold water, that temperature change mixed with the thinning steel resulted in this rupture that flooded the turbine and damaged surrounding structures on the riverbank. This one is an older one. This is not a Kleinschmidt related project, but penstock joints failed due to lack of maintenance and inspection. Water entered the valve building, which is what you see kind of here. And then if you go to the next slide, you can see an outside view. And essentially over 3,000 CFS of water was coming through this pipe. It damaged the powerhouse, as you can see, very similar to that colored photo I showed earlier, where it took off the side, damaged the parking lot, the maintenance shop, and 5 workers were swept into the river and 4 of them drowned. So this was when there were a lot of people around because they were doing work. If a station's unmanned, you might not have any risk of life, but it can take even longer to get there and shut your head gate and react to something like this. So what we just want to advocate through this presentation and our paper is trying to get a more proactive approach instead of a reactive approach. And that can save a lot of time for downtime. It can possibly save a lot of cost in terms of outage duration and costly replacements if you're just doing maintenance and repairs going through a systematic approach.
Thinking about Penstock failures a bit more and having a systematic approach, we want to think about the four main modes of failure for our Penstocks. They include shell tensile rupture, general buckling collapse, local buckling that would lead to shell cracking, and then numerous types of support or foundation failure. We'll talk about those in a little more detail. So shell tensile rupture, as you see a few examples here. We think about this as high internal pressures that create excessive hoop stresses, and then we have tensile rupture in either the shell base material or in the longitudinal joints, whether they be riveted, welded, even bolted. And then, so you'll see a couple of examples on the top right where the shell material, the base material failed. On the bottom left, you see a welded joint that failed. That one was kind of a poor weld quality from our research. But general corrosion and pitting can also cause tensile rupture of the shell and the base material. You'll see kind of a uniform pitting on the bottom picture on the interior of that steel penstock, and then similar on the right side, you have some localized bands of pitting that could cause failure at that location. A good picture here of a kind of a global general buckling collapse. So this failure mode generally occurs for above ground penstocks with potential vacuum pressures on the interior. Could be caused by vents or inadequate venting due to potential ice buildup or valves not providing that vacuum break, or if they're inoperable. Buried penstocks can have similar failures, typically caused by higher than normal groundwater water table elevations, higher surcharge loads, as well as just deterioration of the penstock. Local buckling can be seen in a couple examples here, where the small area of the shell is overstressed. The Zeke stress is the stresses at the horn of the saddles, where there's local deformation of the shell, and that's going to propagate into cracking of the shell. So example of that could be support on the saddles as shown here. Other examples could be concentrated loads on the crown of the penstock, or shallow buried penstocks. That could be heavy vehicles or other point loads at the crown of the penstock, as well as trees or rocks on the top, or rocks protruding up from the bottom of the penstock. A couple more examples of potential failure modes for the penstock. We see on the top right picture a ground support failure of the penstock. This wood stave penstock hasn't failed, but its slope and the support has been washed away. That could be just a slope failure. It could be erosion, and then leading to inadequate support of the penstock. And at some point, there won't be enough support for the penstock or the penstock will be unable to span that opening. Other saddle supports, see this quite a bit of deteriorated concrete, so freeze thaw leading to spalling and cracking of saddle supports. Steel saddle supports, corrosion, loss of section, very common for a lot of penstocks. So again, kind of wrapping that back in, thinking about these failure modes go into a Penstock safety program. So again, to try and create a proactive approach to taking care of our structures. So this safety program, again, is site-specific, structure-specific. So we look at the site, the potential failure modes of this Penstock, which one is more likely, how much deterioration do we have at this point, and what do we need to look at going in the future, and how do we do that?
So let's talk about some best practices for establishing, starting, and then carrying out that Penstock safety program. The first step is to establish those baseline conditions, including your primary risk and safety factors. So this is an analysis of your Penstock, because likely they were designed, 50 years ago, 80 years ago, 100 years ago, to different standards. So where are they by today's standards? How thin is that steel? What type of laminates do we have in our FRP pipe that was installed 40 years ago? We're looking to collect that type of information and then run an analysis to establish what our current factor of safety is. Is it a 2.0? Is it a 1.5? Are we down at a 1.1? And based on those safety factors, we wanted to establish action levels, like when should certain maintenance be done as your Penstock or stuff starts to deteriorate, or pull out threshold levels as in we need to completely repair or replace this Penstock if we get past a certain point. Once we've created those once we know that baseline, we move on to creating an inspection and monitoring program, and a way to consistently document how those key metrics and the primary risk of your Penstock. So we need to know, how often we want to inspect it, what type of inspections are going to need to be done, and if it's steel, it's good to try and take those UT thickness readings in consistent locations so you can compare data from one year to the next, because your steel doesn't necessarily thin at exactly the same rate, so you don't want to be taking it in completely different places every 10 years because you're not going to be able to compare those numbers as well. And then you need to implement that program that you've developed for inspection, and if repairs are recommended, either based on what your operators are seeing or what your consultants are seeing, you want to enact those repair and maintenance programs. And then as you go and you're doing the safety program and you're getting repeat data, you can confirm that validity of that program and see how it's going, and you can see how it's possibly extending your life of that Penstock site by repeat repairs, monitoring, and maintenance. And you're hopefully you can extend your service life quite a long time if you're just proactive about this. Next slide. So right here, Keenan and I are both from the state, so we talk about FERC requirements for high hazard potential, but just want to mention that to the best of my understanding, the CDA guidelines do not have any requirements on Penstock inspection or frequency, but what we're seeing from FERC is if your Penstock has a high hazard potential, you want a detailed inspection every 10 years with an engineer with 10 years experience in Penstocks. And the hydro facilities at low hazard sites, your frequency can be based on your engineering recommendations. If your Penstock's fairly new, it's in great condition, you don't need to do it every 10 years. It can be 20 years, it could be 30 years even for that detailed inspection. Also, USBR has some recommendations, and they actually recommend 5-year inspections, but those might be a little bit more general and just kind of data collection and don't need to be quite as detailed. In addition to those detailed inspections, we recommend exterior visual observations, either weekly or monthly, depending on your Penstock site and the hazard conditions around it. And then also going out after non-normal events. This can be a seismic event, a windstorm where trees might be knocked down, or changes in your pipe operations. You're monitoring the flow through your pipe. If your flow abruptly drops, even if it comes back up, you'll want to check in on it. An example of this is up in Ontario, there was a pipe that was encased in concrete, and the joint on it failed, allowing the water to go up between the pipe shell and the concrete above it, and it collapsed the pipe. So there was a drop in the performance seen at the turbine and the flow coming through temporarily while that was happening. But after that pipe completely collapsed, the Penstock opening technically opened back up to almost its full cross section, and they got back to near normal conditions. But they saw that, they stopped operations, went in and found that collapsed steel, so then they repaired it and got it back online. But that's why after atypical operations, even if you can't visually see anything, you still want to dewater your Penstock, go in and check it out.
I'm going to talk about a few common myths about Penstocks in general. So we'll talk. Penstock inspections are simple and straightforward. It's common myth number one. I've been involved with many comprehensive inspections that are fairly complex, and all inspections require some level of planning. So Penstock inspections, typically, if we're getting on the interior, are going to require confined space entry, where you need the inspection team, but also support teams that you need to plan for. Obviously, we're planning for the safety of the inspection team and how to perform the inspection safely. We're going to talk about access and what we're going to measure and what the goals of the inspection are. And all of that, and we're going to communicate that with the site owner or operator, so that we're making sure our expectations of the inspection are in line with each other. Other part of the inspection that could be, make it complex, it could be many types of advanced technologies being used. Obviously, typically for steel Penstock, we're using ultrasonics to measure steel thickness. Other NDT methods can be used as well, including ground penetrating radar. LiDAR can be used to look at geometries. And then we could use other remote operated vehicles where it's harder to get engineers or inspectors into certain areas. We can get underwater inspection techniques and technology as well. So like I said, we should have a plan for all inspections. We call that our inspection and safety plan. Again, sometimes those can be separate documents. But we talk about safety as in how we're going to access the site, who's going to be accessing for the inspection, and what they're going to be doing, and then who are they going to be supported by, and what are other safety measures needed to be in place to make that work. Inspection plan is going to talk about, obviously what the goals of the inspection are, what we're anticipating for measurements, and what kind of data we're going to collect, and how we're going to be able to use that in the future, making sure that, again, that we're in line with the expectations for the owner as well as the inspection team. Talk about communication and how the actual inspection is going to take place. Overall, the goal is to identify issues ahead of time, right, and make sure we have a way to deal with any issues that could arise, and therefore creating a cost-effective, ideally and safe inspection, and that can detect any problems that we anticipate coming through.
Common myth number 2 is that exterior inspections are enough to identify key issues, especially if your Penstock is exposed along its full length. While it is true that external inspections can identify a lot of the key issues, you can see your foundations, you can see your exterior coating, you can look at expansion joints and see if they're allowing for that temperature movement. You can see a lot of things, but the fact is that interior always looks much different than the exterior. Exterior typically gets more maintenance, it gets repainted more frequently, and it's also not subject to continuous water coming through that have silt and debris and could be somewhat corrosive to the interior. So you really do want to, in a detailed inspection, dewater, go in and take a look. You can see pitting, you can see rusting, corrosion. On FRP, you might see delamination. Those saddle stresses, Keenan showed a picture earlier about showing that steel penstock with that stress and that deformation around the horn. You might see deformation from the outside, but you might go inside and find that that's actually causing some cracking. That cracking just hasn't come out on the outside yet. So if you can, every so often, dewater your penstock and go in and do a detailed inspection in there as well.
Common myth number 3, expanding on what Jill just talked about, buried and exposed penstocks require similar methods. While we can do a lot of things on either side and get a lot of information, like Jill said, you know, the inspection that I would do for a buried penstock is going to be different than one that's kind of elevated or above ground. You know, for example, an above ground steel penstock on saddles, you know, I would spend a lot more of my time on the exterior where it's, you know, either safer, I can see a lot, I can look at the coating, I can look at supports, I can take a lot of thickness measurements from the exterior and looking at the shell thickness. But I'm also going to get back, I want to get back inside the penstock and again, look at surface corrosion potentially or coating condition on the inside, pitting, you know, rivet, if it's a riveted penstock or welds. Buried penstocks don't allow you to do that, where you're going to spend 90% of your time on the interior and you got to take all your measurements from the inside or be looking at just the inside and kind of extrapolating the condition without it. But you get some signs of leakage potentially for buried penstocks by looking at saturated grounds potentially if the penstock's been recently dewatered. So it can be slightly different looking at different things, different at exposed versus buried penstocks.
Common myth number 4 is that inspection approaches are similar across all materials. You've heard both Keenan and I mention ultrasonic thickness readings for steel. That's a very common way to tell your steel thickness, but you're not going to take UT readings for concrete or your fiberglass, your FRP, or high density polyethylene pipe, HDPE, or wood. You're only going to use that UT gauge really for your steel. At concrete, you're looking more at visual inspections of your concrete, and your baseline inspection is going to mean a lot of sketches of cracking and other deterioration and a lot of photos to document very specifically different locations where this is occurring, so that when you come back in 10 years or whatever your time frame is, you can look at that and see how long those cracks have gone, if they're widening. You're doing a lot of baseline visual comparison with concrete. You might use some penetrating radar scan of your concrete when you first do it to figure out rebar, wire mesh, and concrete thickness, especially on a buried pipe when you're establishing that baseline, but that's not something you would need to do for subsequent inspections because that's not really going to change on a concrete pipe. Wood, you might take some bores of the wood itself to see how soft the wood is, and if it's deteriorating, you can visually see deterioration really well. You're looking at your bands and how much corrosion they have, your saddles and your foundations. FRP, you're looking a lot of visual inspections. You're looking for signs of delamination. Some newer FRP pipes can have an outer colored coating that once it wears away, you know you're getting into your fibers and your structural components, so it's time to make repairs. Older pipes won't have that. So you're looking for, again, signs of delamination, signs of wear and abrasion, and stuff like that. And with FRP, you just want to know that sometimes that movement from okay to possible failure can occur more quickly than what you might see with steel or concrete. HDPE pipe, again, it's a visual inspection, and you're really focusing on the joints. Those electrofusion joints, you're looking for UV damage if any part of that HDPE pipe has become exposed, and signs of possible thermal stresses if it's not allowed to move and expand like it wants to.
Common myth number 5, repair is always more economical than replacement. Obviously, that's not always the case. You know, sometimes replacement is the more economical solution, as are structures and age, right, their cost of maintenance continues to rise, and at some point there's a tipping point. Part of that is understanding what our structure's condition is, right? We want to know where its limits are. We want to know what the actual what the condition is there. So, you know, if there's a pinhole in a steel structure, can I just repair it? You know, but can I just repair it with a patch, welding a steel plate, or do I need to go and repair or replace the whole section of that steel penstock? Obviously, that decision comes down to one, obviously, costs and how they start to ramp up, but replacement costs depend on location, you know, material, and, you know, site-specific circumstances, including geological, geotechnical considerations, and other access considerations.
With this forward-looking approach that we're advocating, it becomes very important that you have good design partners for both building your safety program, establishing your baseline, and then going forward with maintenance and repairs, and eventually down the road, replacement. And this whole program that we hope you develop is only going to be as useful as the people both helping you build it, both internally and externally, and also the professionals conducting it. Next slide. So I don't want to do a sales pitch on this. Obviously, Kleinschmidt hydroelectric structures, Penstock is the key component of what we do on a daily basis, and we do have a lot of experience, but so do other consultants. There's a lot of good people with a lot of experience out there for you guys to talk to. We just want to make sure that whoever it is, you're getting the support you need to protect your penstocks, protect your facilities, and, you know, protect yourself. So, you know, our recommendations to look for is a lot of experience, senior level expertise, industry-specific certifications where needed. If you're doing a steeply inclined penstock, or if you're kind of moving into your surge tanks and complete vertical, you might want SPRAT or IRATA certification so they can be, your inspector can be up there climbing around with your technical people who also can do it and take readings. Maybe a coating specialist or a metallurgy specialist. There's a lot of different certifications out there that can bring value to your program and what you're trying to do. You want to make sure that everything is comprehensive, forward-thinking, and not just immediate inspection services. You can hire technicians who can come out and take UT readings of your entire structure, but they can't then analyze your structure and evaluate its service life and understand what needs to be done to keep it running. Next slide. So, and there's also a whole lot more components in the analysis than we've just talked. And I have a whole list here, but it expands from hydraulic transient analysis that engineers can help you to, system risk analysis, repair and replacement options. You can do in-kind replacements. You can switch materials when you replace. You can do repairs with steel plate. You can do FRP, wet layup on your pipes. There's a whole bunch of things out there for you to do, and having an expert involved will help open you up to many options. And then if you do go down the path of design or replacement, you've got drawing packages, calculations, technical specifications, permitting assistance, wetland delineations if you're obviously near bodies of water, bidding assistance and construction of surfaces, record drawings at the end of it to document what's been done. There's a lot of things that can go into your penstock repair or replacement, and finding that right partner and teammate is just going to help you extend your penstock service life that much more.
So to wrap up, again, looking forward, if I was an owner or a manager, I want to ask myself, when was the last time I took stock of my penstock, right? What potential issues are out there that I may have overlooked? Are there things that I have I haven't prioritized or that aren't quite prioritized correctly. And also, are there things out there that I can do now that might limit or, pull back on delays to operations? Can I limit excessive repair costs or try to prevent things that could potentially be worse? So with that, we kind of wrap things up, and we thank you for joining us today. Again, I'm Keenan Goslin, and Jill Davis is here as well. We'll take some questions now. I think if you push the raise your hand button, you can ask a question, or I don't know if you type them in, we can see those as well.
Yeah, thanks, Keenan. It's Janelle. So we do have one question again. As Keenan said, if you have a question, type it into the question box or raise your hand, and I will open up your line. So the one question that we have, and perhaps you can provide your advice on this, what types of corrosion protective coatings are preferred for penstocks, both interior and exterior? Do you have any advice on that?
Typically, the first step in corrosion protection is going to be your coating system. It can be a polyurethane-based or a epoxy-based coating. If it's steel, concrete, you're not so worried about that. And FRP and HDPE both have their own corrosion protection built right into it. And then, with steel penstocks, especially if you're transitioning from buried to exposed or you have a manhole sticking above, you might want some local cathodic protection to help you out as well.
Okay, great. Thanks, Jillian. So any other questions? Again, use the question box or raise your hand and I'll unmute your line. We'll give folks a couple minutes here in case there's questions. Don't be shy. Okay, I'm not seeing any other questions. So as I mentioned at the outset, we have recorded this presentation. Kleinschmidt has agreed that we will be able to share the presentation in the recording. So we will make that available to participants probably sometime later next week. Following this, you will receive a survey. So if you have any input for the OWA or questions for Kleinschmidt, I'm happy to share those questions with them as well. And I think that's it for me. So I just really want to thank both Jillian and Keenan. I know you put a tremendous amount of work into preparing this presentation. Really thank you, and I found it very informative. So thanks again.
Great.
Thank you for having us. We appreciate it.
Yes.
Okay, great. And wishing everyone a safe and happy weekend. Take care.
Take care.